Welcome back, everyone, to another deep dive. And today we're tackling a pretty hefty one.
Yeah, this one's a bit of a monster, isn't it?
It is. It's Douglas Hofstadter's Gödel, Escher, Bach. You familiar with
Oh yeah, definitely a
a
classic.
classic and a bit of a mind bender, right? But that's what we're here for today. We're going to try to break down some of the key ideas, kind of give you a sense of, what the book is about, what makes it so special. So, even if you haven't read the whole thing, you can still get a taste of its awesomeness.
Absolutely. It's a book that rewards multiple readings, for sure. But even on a first pass, there are some truly amazing insights to be found.
Totally. So where do we even start with a book like GEB? I mean, it's got math, it's got art, it's got music, it's got like Zen Buddhism, it's all over the place.
Right. That's part of what makes it so unique, though. It's not just a book about those things. It's a book that does those things. It weaves them together in a way that creates its own kind of strange loop.
Totally. So think about like Bach's musical offering. Have you ever listened to that?
Oh, yeah. Many times. It's brilliant.
It is. It's incredible. So
Yeah.
Bach goes to visit King Frederick, and the king gives him this like musical theme and says, hey, improvise on this. And Bach takes that theme and spins it out into all these incredible variations.
Like he takes that one little idea and explores all its possibilities. It's like a master class in musical creativity.
Exactly.
Mhm.
And Hofstadter uses that as a model for the whole book. He calls GE a meta-musical offering. He's taking these big ideas, these themes, and showing how they connect and interact in surprising ways.
And just like Bach's musical offering, GB has this incredible structure, this intricate layering of ideas that mirrors those musical forms, fugues, canons, all that good stuff.
Exactly. And right from the start, he sets up this idea of self-reference. Like the very title of the book, Gödel, Escher, Bach, it's a self-referential loop. It's about systems that can talk about themselves, point back to themselves.
And Bach himself does this in the musical offering. He puts a hidden message in the inscription, using the initials to spell out Reiserkar, which means to seek. It's like he's hinting at all the hidden depths waiting to be discovered.
Oh, that's right. And he uses the word canonic in a double sense, right?
Yeah, it refers to the musical form of canons, but it also means in the best possible way. So there's this playfulness, this ambiguity right from the get-go.
So you've got this self-referential structure in the book, but it's also reflected in the content itself. Like Escher's art. You've got those classic images like drawing hands, where hands are drawing each other, or print gallery, with that impossible architecture that loops back on itself.
Yeah, those strange loops are a key theme throughout the book. It's about those situations where you've got these levels, these hierarchies, but they somehow fold back on themselves, creating these paradoxes and puzzles.
Like the Epimenides paradox, right?
Ugh.
This statement is false.
Exactly. It's a classic example of a self-referential loop that creates a logical contradiction. And Escher captures that visually in works like Ascending and Descending, those staircases that seem to go up and down forever, but always end up back where they started.
It's like you can walk up them forever, but you never actually get anywhere.
And it's interesting, those impossible staircases, they were actually inspired by mathematician Roger Penrose. It was his concept of the Penrose stairs that Escher adapted for his artwork.
So even there, you've got this interplay between math, art, and logic. They're all feeding into each other.
Absolutely. And these paradoxes, these strange loops, they weren't just seen as curiosities, they actually had a big impact on the development of mathematics and logic in the early 20th century.
Oh, yeah, I remember reading about that. It's like people were starting to realize that the foundations of math weren't as solid as they thought.
Right. These paradoxes in set theory and logic led to a lot of debate about how to define the basic concepts of mathematics and how to make sure that the systems we use to reason about those concepts are consistent and don't lead to contradictions.
So, like, if you can't even be sure that 1 + 1 = 2, then what can you be sure of?
Exactly. It led to a whole movement trying to formalize mathematics to find a way to express it in a purely symbolic language with clear rules so you could, prove things without ambiguity.
And that brings us to chapter 2, right? The MU puzzle. I remember struggling with that one.
Yeah, the MU puzzle is a great example of how formal systems work and how even simple rules can lead to surprisingly complex results.
So remind me, what was the MU puzzle again?
Okay, so you've got this system with just 3 letters, M, I, and U. And you've got 4 simple rules for transforming strings of these letters. Like you can add a U to the end of any string that ends in I, or you can double the string after an M, stuff like that.
Okay, I vaguely remember that. And the challenge was,
The challenge is, starting with the string MI, can you produce the string MU by applying those rules.
And it seems like you should be able to, right? Just shuffling those letters around.
Yeah, it feels like with enough manipulations you should be able to get there. But the surprising thing is, you can't. No matter how many times you apply those rules, you'll never be able to produce mu from mi.
Really? That's wild. So how do you even figure that out? Like, do you just keep trying different combinations until you give up?
Well, you could do that, but there's actually a more elegant way to solve it. It involves understanding the structure of the rules and how they affect the number and order of the letters in a string. You start to see that there are certain patterns that are preserved by the rules, and mu simply doesn't fit those
No.
patterns.
So it's not just about blindly applying the rules. It's about understanding the underlying logic of the system.
Exactly. And Hofstadter uses the mu puzzle to introduce this idea of different modes of thinking about formal systems. You've got the mechanic mode where you're just blindly following the rules like a machine. Then there's the intelligent mode where you try to step back and understand the deeper structure of the system. And then there's even the unmode, which is more of a Zen approach, letting go of the need to control the system and just seeing what emerges.
I like that, the unmode. It's like just let go and trust the process.
Right. And the MU puzzle shows that even in a seemingly simple system, there can be these hidden constraints, these limitations on what's possible. It's not just about the rules themselves, it's about how they interact and the overall structure they create.
Chapter 3 is kind of a quick one, right? Figure and ground. It's more about how we think about logic and arguments.
Yeah, it uses the Achilles and the tortoise dialogue again, this time to explore the idea of accepting logical implications.
Oh, yeah, the tortoise is always trying to get Achilles to spill everything out,
Yeah.
right?
Exactly. This time, the tortoise keeps pushing Achilles to explicitly agree with every single tiny step in a logical argument, even the implication that one step follows from the previous ones. It becomes this infinite regress of needing to accept that one thing leads to another.
I remember that. It was like, okay, so you agree that A implies B, but do you agree that A implies B? It just keeps going.
And it seems silly, but it actually points to something important about how we reason. We often take for granted that we agree on the basic rules of logic, that we both accept that if A implies B and A is true, then B must also be true.
Right. We don't usually stop to question every single link in the chain of reasoning.
And that ties back to the MIU system. In that system, there's no interpretation, no meaning assigned to the symbols. We're just following the rules of manipulation. So there's no need to question the why behind each step because there's no inherent meaning to latch onto.
Okay, that makes sense. So Chapter 4 introduces another formal system, the PQ system, which is all about representing addition.
Right. It's another example of how we can use a simple system with a few basic symbols and rules to capture a complex mathematical concept.
So how does it work? Remind me.
Okay, so in the PQ system, you've got hyphens, the letter P, and the letter Q. And a string, like, say, x, p, y, q, z, is supposed to represent the statement x plus y equals z.
So the hyphens stand for the numbers, and the P and Q are like the plus and equal signs.
Exactly. And the system has an axiom, a starting point, and a rule for generating new theorems. And the cool thing is, every true addition statement can be translated into a theorem that you can derive within the PQ system, and every theorem corresponds to a true addition.
So it's like a perfectly self-contained little world of addition, captured in this formal language.
Precisely. And it shows how you can create a formal system that's both consistent, meaning all its theorems are true under interpretation, and complete, meaning every true statement within its domain can be proven within the system.
Okay, that's pretty neat. And Chapter 5, Recursive Structures, dives into recursion, using Euclid's proof of the infinite number of primes as an example.
Yeah, Euclid's proof is a classic example of recursive thinking in mathematics. It's elegant, it's powerful, and it demonstrates how you can use a concept to prove something about the totality of things that possess that concept.
Remind me how it works again. It's been a while since I've thought about prime numbers.
Okay, so the basic idea is you start by assuming that there are only a finite number of primes. Then you use that assumption to construct a new number that's bigger than all the primes you assumed existed. And you show that this new number is either itself prime or it's divisible by a prime that wasn't in your original list.
Oh, I see. So either way, your original assumption that you had all the primes is contradicted.
Exactly. And because you can repeat that process indefinitely, you're forced to conclude that there must be an infinite number of primes.
Okay, that makes sense. And the recursion comes in because you're using the concept of primality within the proof about the totality of primes.
Right, you're sort of calling on the concept of primality within itself, which is a hallmark of recursive thinking. And Hofstadter points out that we accept this proof because we trust the reasoning, not because we can actually count infinitely many primes.
Right, it's a logical proof, not an empirical observation.
Exactly. And that chapter also talks about the idea of generalization in mathematics, which is another important concept.
Remind me what that means again.
So generalization is when you take an argument that works for a specific but arbitrary number, say n, and then realize that because n could have been any number, the argument holds true for all numbers. It's a way of moving from a specific case to a general conclusion.
Okay, that makes sense. So, like, if you can prove something is true for any number n, then it must be true for all numbers.
Exactly. It's a powerful tool for making universal statements in mathematics.
Chapter 6, Capturing Compositeness, is all about trying to formally represent composite numbers.
Right. Yeah, it introduces the TQ system, which is similar to the PQ system, but this time the goal is to create theorems that tell you whether a number is composite, meaning it's not prime.
Oh, so instead of defining primes directly, we're defining everything that's not prime.
Right. It's a shift in perspective, a way of looking at things from the other side. And the chapter throws in a little puzzle about a specific number sequence and how it relates to the idea of figure, 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 hinting at the challenges of defining something in terms of what it is versus what it is not.
It's like sometimes it's easier to define something by what it's not, but that doesn't always give you a complete picture.
Exactly. And chapter 7, primes as figure rather than ground, then flips that idea and tries to formally represent primes directly.
So now we're back to focusing on primes themselves.
Right. This chapter introduces a system based on the relation does not divide, or DND. There's an axiom stating that any number x does not divide itself, which is true in a sense because the result wouldn't be a whole number greater than 1. And then there's a rule that lets you build up statements of non-divisibility. The puzzle then becomes why we can't prove certain true statements about non-divisibility within this system.
So even though we have a system for representing primes, it's not powerful enough to capture all the truths about them.
Right. It highlights the limitations of formal systems and how even seemingly simple concepts can be tricky to define completely and consistently.
Okay, chapter 8, Typography, is a bit of a break from the formal stuff. It's another dialogue with Achilles and the tortoise, this time involving a record player.
Yeah, it's a classic self-referential paradox presented in a playful way. You've got this record labeled, I cannot be played on record player. And every time the crab builds a supposedly perfect record player, this problematic record causes it to break.
It's like the record is designed to sabotage any record player that tries to play it.
Exactly. And the eventual realization is that a system designed to handle any self-referential instruction might be inherently impossible. It's a lighthearted way of introducing the limitations that self-reference can impose.
Chapter 9, Consistency, Completeness, and Geometry, dives back into the core concepts of formal systems, using the PQ system again and drawing parallels to geometry.
This chapter is all about exploring what happens when you change the interpretation of symbols in a formal system. By reinterpreting the meaning of Q in the PQ system from equals to is greater than or equal to, previously false theorems become true.
So just by changing the meaning of one symbol, you can change the truth value of statements within the system.
Exactly. It highlights that the meaning we assign to symbols is crucial, and that a formal system's consistency and completeness depend on that interpretation.
It's like the system itself doesn't care about truth or falsity, it just follows the rules. It's up to us to decide what those rules mean.
Right. And that chapter also talks about how the definitions of terms in a formal system can be embedded within the axioms themselves, acting as implicit definitions. This idea was central to the development of formal geometry.
And it also discusses the difference between internal consistency, where a system's theorems are true within its own little world, and external consistency, where they correspond to truths about the real world.
Right. For math, those two types of consistency tend to converge, but it's an important distinction to keep in mind.
Chapter 10, Levels of Description and Computer Systems, uses another record player analogy to illustrate the idea of feedback loops and how problems can arise from interactions within a system.
Yeah, this time it's a record labeled canon on BACH, but it gets distorted by feedback. The idea is that the feedback, which is a consequence of earlier events in the story, interferes with the proper playback of the record.
So even if the record itself is fine, the way it interacts with the record player can create problems.
Exactly. It's about how complex systems can exhibit behaviors that aren't immediately obvious from looking at their individual parts in isolation. You need to consider the interactions, the feedback loops to understand how the whole system behaves.
And you need to be able to test both the record, the formal system, and the record player, or reasoning,
Yeah.
separately to figure out where the problem lies.
Right. It's like debugging a complex system. You need to isolate the different components and see how they influence each other.
Okay, Chapter 11, The Little Harmonic Labyrinth, is a bit of a wild ride. It's another dialogue with Achilles and a genie, and it involves meta-wishes and a fall into the pit of the evil Magitor.
It's definitely one of the more whimsical chapters in the book, a bit of a break from the heavier formal stuff.
So Achilles is trying to outsmart the genie and get more than the usual 3 wishes.
Yeah, he's trying to figure out if he can wish for more wishes, a classic meta-wish scenario. And the genie is being deliberately vague, but hints that it might be possible. Then things take a turn for the surreal with the popping tonic and the fall down the stairwell. It's almost like a dream sequence, full of strange imagery and unexpected turns.
Chapter 12, Recursive Structures and Processes, dives back into recursion, this time looking at music and introducing recursive transition networks.
This chapter explains musical modulation, which is the process of moving away from and returning to a home key. It uses an example from Bach to show how what sounds like a resolution might actually not be, creating a sense of delayed gratification or even heightened tension. Then it introduces RTNs, which are like flowcharts for creating grammatical phrases.
I remember those. They're a way of representing language structure in a visual hierarchical way.
Exactly. And the recursion comes in because you can have one part of the network calling on another part, which can even call back on itself. It allows for the creation of complex, nested structures like you see in natural language.
So you can build these intricate structures from a relatively small set of rules just by allowing them to call on each other recursively.
Right. And that chapter also connects this idea of recursion to how computers might define the best move in a game like chess, using a recursive algorithm that considers the opponent's best response and so on.
It's like a mind game within a mind game.
Exactly. It's recursion all the way down.
Okay, Chapter 13, Bloop and Floop and Gloop, has another musical experiment, this time with the tortoise playing BACH, cage, and a jumbled version of BACH.
Yeah, it's another example of how transformations can reveal unexpected connections. Achilles observes that a specific musical transformation turns BACH into cage, and that same transformation turns cage into the jumbled BACA. It's like a cycle or maybe a commentary on the relationship between different musical styles.
And it ties into this broader theme of how systems can be related to each other through transformations, whether it's musical notes, formal systems, or even biological organisms.
Absolutely. It's about seeing the patterns and connections that emerge when you apply a consistent set of rules to different starting points.
Chapter 14, Meaning and Form, gets into the philosophical question of whether meaning is inherent in a message or if it requires an interpreter.
It's a deep question that has implications for how we think about communication, language, and even consciousness.
So is it like a message only has meaning if there's someone there to understand it?
That's one way to look at it. The chapter uses the example of deciphering ancient texts. We often feel like those texts have meaning even before we know what they say.
Like we assume there's a message there, even if we haven't cracked the code yet.
Right. But the chapter also raises the possibility that there could be forms of communication that we wouldn't even recognize as such, simply because they're so foreign to our ways of thinking. It challenges us to consider what we mean by meaning and whether it's truly inherent in a message or if it requires an interpreter to bring it out.
It's like if a tree falls in the forest and no one's around to hear it, does it make a sound?
Exactly. It's a question of whether meaning exists in the world independently of our minds or if it's something we project onto the world.
Chapter 15, The Propositional Calculus, introduces a formal system for dealing with logical propositions.
This chapter marks a return to the more formal side of things. The propositional calculus uses symbols to represent logical connectives like not and or and implies. It has a set of axioms, starting points, and rules for deriving new theorems.
So it's a way of representing logical arguments in a symbolic language, kind of like a mathematical notation for logic.
Exactly. And the amazing thing is that by just manipulating these symbols according to the rules, you can derive logically valid conclusions, even if you're not consciously thinking about the meaning of the symbols.
That's like you can do logic without actually thinking about it.
Right. It's a purely mechanical process, but it demonstrates the power of formal systems to capture the essence of logical reasoning.
Chapter 16, Typographical Number Theory, or TNT, takes that idea and extends it to number theory.
TNT builds on the propositional calculus by adding symbols for numbers, arithmetic operations, and quantifiers. It aims to create a formal system that can express all the truths of arithmetic.
So, like, statements about prime numbers, addition, multiplication, all that stuff.
Exactly. And it uses rules of inference, including induction, which is a crucial principle for reasoning about infinite sets like the natural numbers.
Okay, and that chapter also discusses Hilbert's program, right?
Yeah.
The ambitious goal of finding a complete and consistent set of axioms for all of mathematics.
Right. Hilbert was hoping to find a foundation for mathematics that was so solid, so rigorous, that it would be impossible to derive contradictions from it. But Gödel's work showed that this dream was ultimately impossible.
And TNT plays a key role in Gödel's proof, right?
Absolutely. Gödel's incompleteness theorem relies on the fact that TNT is powerful enough to represent its own statements through a process called Gödel numbering.
Okay, remind me how that works again.
So, Gödel numbering assigns a unique number to every symbol and every string of symbols in TNT. This allows you to talk about statements within TNT by referring to their Gödel numbers.
So it's like a code that lets you translate statements about the system into statements within the system itself.
Exactly. And this self-referential capability is crucial to Gödel's proof. He constructs a sentence within TNT that essentially says, I am not provable within TNT.
And that's where the incompleteness comes in, right?
Right. If that sentence is true, then it means there are true statements within TNT that can't be proven. And if it's false, then TNT is inconsistent.
So either way, there's a fundamental limitation to what TNT can do.
Exactly. It shows that even a formal system as powerful as TNT can't capture all the truths of arithmetic.
Chapter 17, Human and Gödel, connects this idea to a Zen koan, which is a kind of paradoxical story or question used in Zen Buddhism.
Yeah, it's a surprising juxtaposition, but it highlights the deep philosophical implications of Gödel's work.
So what's the koan about?
It's a story about a master who tells his student that there's no such thing as a trainable mind or a findable truth. And the student is confused because, well, that's what they're trying to do, train their minds and find truth.
It's like saying the goal of your quest is to realize there is no goal.
Exactly. And it connects to Gödel's work because it suggests that there are limits to what we can know, even within a seemingly well-defined system like mathematics.
So even if we have perfect logic and a perfect formal system, there are still truths that are beyond our reach.
Right. It challenges us to consider the nature of truth itself and whether it's something we can ever fully grasp through formal systems.
Chapter 18, Artificial Intelligence, retrospects, takes a step back and looks at the history of AI and some of the challenges it's faced.
Yeah, it revisits the idea of the perfect record player from earlier chapters and how the tortoise's self-referential records always seem to find a way to break it. This reflects the early struggles of AI to deal with self-reference and to create systems that could handle all possible inputs and situations.
It's like every time they thought they had a system that could handle anything, the tortoise would come up with a new trick, a new paradox that would break it.
Exactly. And the chapter also discusses early chess programs and how simply looking further ahead in the game than humans wasn't enough to make them unbeatable. It turned out that human chess masters rely more on pattern recognition and a deep understanding of the game than on brute force calculation.
So it's not just about processing power. It's about the way you represent and understand the information.
Right. It suggests that true intelligence requires more than just the ability to follow rules and crunch numbers. It requires a higher level understanding of context, meaning, and strategy.
Chapter 19, Artificial Intelligence, Prospects, looks ahead to the future of AI and discusses the importance of programming languages and levels of abstraction.
This chapter argues that higher-level programming languages are crucial for AI research because they allow us to think in terms of larger, more meaningful chunks of information rather than the very low-level instructions of machine code.
So it's about building with bigger, more conceptual building blocks.
Exactly. And the development of new programming languages has often been tied to advances in AI, providing the tools to express more sophisticated ideas and algorithms.
It's like the language you use shapes the way you think, so having the right language is essential for progress in AI.
Right. And that chapter also discusses the idea of nearly decomposable systems from physics as a model for how complex AI systems might be structured.
Remind me what those are again.
So a nearly decomposable system is one where you've got these modules that interact weakly with each other. It's like a football team. where each player has their own role and skills, but they also need to coordinate and communicate to achieve a common goal. Or like an atom, where the nucleus and the electrons have their own internal dynamics, but they also interact to create the overall structure of the atom.
So you can have these different levels of organization within a system, each with its own rules and behaviors, but they also need to interact in a coherent way.
Exactly. It suggests that a truly intelligent system might be organized in a similar way, with different modules specializing in different tasks, but also working together seamlessly.
Chapter 20, Strange Loops, or Tangled Hierarchies, is all about how different levels of a system can become intertwined, creating those paradoxical loops that are so central to the book.
This chapter really gets to the heart of what GAB is all about. It starts with a discussion of holism versus reductionism, the age-old debate about whether we should study systems as wholes or by breaking them down into their parts.
And Hofstadter introduces the Zen concept of mu, right?
Yeah, mu is a kind of answer that unasks the question. It's a way of stepping outside the dichotomy of holism versus reductionism and seeing that both perspectives have their limitations.
It's like saying the answer is neither yes nor no, it's something else entirely.
Exactly. And the chapter then revisits the crab canon, showing how a musical piece can be self-referential by playing the same melody forward and backward simultaneously.
It's like a musical Mobius strip.
Right. And then it goes on to discuss the complexity of ant colonies, where individual ants with very limited intelligence can collectively exhibit incredibly complex behavior.
It's like the intelligence of the colony emerges from the interactions of the ants, rather than residing in any individual ant.
Exactly. And that raises questions about how our own brains might work, with billions of neurons interacting to create our thoughts, feelings, and behaviors.
So it's not just about the individual neurons, it's about the patterns of activity that emerge from their interactions.
Right, and that chapter also touches on how our brains process visual information and how we recognize objects, suggesting that there are multiple levels of representation and that meaning emerges from the interaction of these levels.
It's like the image on our retina is just the starting point. Our brains do all this complex processing to extract meaning and recognize objects.
And that chapter ends with this really intriguing thought about how our sense of self might arise from the tangled hierarchy of levels in our brains.
It's like we perceive ourselves as unified beings, but that unity is an illusion created by the complex interactions of all these different parts of our brains.
Exactly. It's a mind-blowing idea.
Chapter 21, The Brain as a Formal System, asks whether we can think of the brain itself as a kind of formal system.
It's a tempting analogy, given that the brain is processing information and following rules. But the chapter explores the challenges of this approach, considering how dynamic and complex the brain is compared to the relatively simple formal systems we've been looking at.
So, how do you represent the firing of billions of neurons as a set of symbols and rules?
Right. It's not a straightforward mapping. The chapter discusses the idea of brain symbol as dynamic entities that can be active or dormant, and it raises questions about the size and nature of these symbols and what they represent.
And it also returns to the ant colony analogy to question where the information for complex behavior really resides.
Yeah, is it in the individual ants or in the patterns of their interactions or in the structure of the environment? It's a question that's still being debated.
Chapter 22, Mind as a Tangled Hierarchy, continues this exploration of the mind, introducing the idea of automatic symbolic universes, or ASUs.
This chapter suggests that our minds might contain these vast, interconnected networks of symbols and concepts where our thoughts and memories meander and connect, often in seemingly random and surreal ways.
It's like a dreamscape, where logic and reason take a backseat to free association and unexpected jumps between ideas.
Right. And the chapter uses the analogy of translating Lewis Carroll's Jabberwocky to illustrate the challenges of capturing this kind of fluid associative thinking in language. It's like trying to map a dreamscape onto a grid.
Chapter 23, The Central Dogma of Molecular Biology, takes a bit of a detour into genetics, starting with a conjecture from the tortoise about prime numbers.
Yeah, the tortoise proposes that every even number is the difference of two odd primes, which is a twist on a famous unsolved problem in number theory called Goldbach's conjecture.
Oh, that one. I remember reading about that. It's one of those simple-sounding math problems that has stumped mathematicians for centuries.
Exactly. And the chapter then shifts gears to talk about the 3n+1 problem, which is another simple-sounding problem that leads to surprisingly complex behavior. It involves repeatedly applying a simple rule to a number, and the question is whether you always end up at 1.
So it's like a mathematical version of the will it blend question.
Kind of. It's a fascinating example of how simple rules can lead to unpredictable outcomes.
And it ties back to the broader theme of emergence, how complex behavior can arise from the interaction of simple elements.
Absolutely. It's a theme that runs throughout GB, from formal systems to music to biology.
Chapter 24, DNA and Protein, continues the biology theme, starting with a humorous dialogue about a missing gold box.
Yeah, it's another one of those interludes where Hofstadter lets his playful side shine through.
But then it gets into some pretty serious stuff, talking about bloop and fluke programs and the ready-ag function.
Right. Blueprint programs are essentially programs that are guaranteed to terminate, while foo programs can run forever. And the ready-ag function asks whether a given bloop program will halt.
So it's like a test for whether a program will eventually finish or get stuck in an infinite loop.
Exactly. And the surprising thing is that this function, which we can understand and apply, can't be computed by any fluke program.
So there are things that we can figure out that computers, at least as we currently understand them, can't.
Right. It suggests that there might be fundamental limits to what computers can do, even if those limits aren't.